Hi everyone, this video is going to review chapters 2 and 3 in your text. The chapters are not very long, and so I'm going to provide you with a brief overview, and you should thoroughly read each chapter, and if you have any questions you should let me know. Chapter 2 covers the organization of information, frequency distributions. And a frequency distribution can really just simply be considered a count of something or a count of observation. So when we set up a frequency distribution, it's usually set up as a table, and in that table we show the number of observation or counts that fall into each category for one or more variables. So for example, this frequency distribution shows different identities of Native Americans and the frequency or count of those individuals. So in the Native American category, we have 947,500 individuals. In the Native American of multiple ancestry, we have 269,700 individuals. And in the Native American of Indian descent, we have 5,537,600 individuals. And the total N, or the total number, if we add all of those frequencies together, is 6,754,800 individuals. So you can see it's just a count, really, of each person in each category. This is another example of a frequency table. So in this example, we are showing people who own iMacs what type of computer they owned previously. And so in this table, we show the frequency and then the relative frequency. So I'm going to explain that. The types of previous ownership are none, Windows, the person owned a Windows computer, or a Windows operating system, I should say, or the person owned a Macintosh with a Macintosh operating system. And so those who had no computers prior to having an iMac, there were 85 people. Windows type computers, 60 people, and Macintosh, 355, for a total of 500. So we know that those frequencies are the counts, but in the column on the far right, there's relative frequency. And the relative frequency we can think of as the proportion of people in that category relative to the total number of people. So 85 people out of the 500 individuals total is 0.17. That's the proportion. 60 people is 0.12. That's the proportion. 355 equals 0.71, and that's the proportion. And then we can see the total is 500, and the total, if we add up all of those relative frequencies, they add up to 1. So again, to explain proportions, a proportion is simply a relative frequency that we get by dividing the frequency in each category by the total number of cases. And the formula for it is P equals F over N. And so that would be P equals F divided by N, or another way of writing it is by using P equals F slash N, which means the same thing, P equals F divided by N. And so the example is that if there are 100 people in a meeting and 35 of them are women, what proportion of these people in the meeting is women? And so the P, we want to get the proportion P, and we are going to divide 35, which is the frequency, F, divided by 100, which is the N, the total number of people. And in that case, the proportion is 0.35. We then can convert the proportion to a percentage. And so a percentage is just the relative frequency obtained by dividing the frequency in each category by the total number of cases and then multiplying by 100. So it's really just calculating the proportion and then multiplying it by 100, and that will give you the percentage. And so in the previous example, we had P equals 35 divided by 100. So the proportion of women in the meeting was 0.35, and to convert that to a percentage, we simply multiply it by 100. So 0.35 times 100 equals 35%. So on the next slide, we can see the percentage distributions, and on this table, it displays the frequency or the count, the relative frequency, which is a decimal, number expressed as a decimal, and the percentage, which is the decimal converted to a percentage. So we'll just go through this quickly. The minimum age in this particular group of individuals, there's a minimum age of individuals who are 14 years old, 15 years old, 16 years old, 17 years old, and 18 years old. So the categories are listed in the first column on the left. In the next column, we see the frequency. So that's just the count, the number of people within each of those categories. So there was one person who was 14, one person who was 15, 9 people who were 16 years old, and 4 who were 17, and 12 who were 18. And the total number of people in the group, there were 27 people. And so again, the relative frequency is a number expressed as a decimal, and we can see that we get that just by dividing the count or the frequency by the total number. So 1 divided by 27 equals 0.037. 15 divided by 27 is 0.037. 9 divided by 27 is 0.333. 4 divided by 27 is 0.148, and 12 divided by 27 is 0.444, and 27, of course, divided by 27 is 1. And then in order to convert the frequencies to a percentage, we just multiply the relative frequency by 100. So 0.037 times 100 is 3.7. And that's the same for individuals who are 14 and 15. If we go down to the 16-year-olds, if we multiply the relative frequency, 0.333 times 100, it's 33.3%. In the next category, 0.148 times 100 is 14.8%. And in the 18-year-old category, 0.444 times 100 is 44.4%. And if we add those percentages together, we get 100% for the entire group. We talked about levels of measurement. There are 4 different levels of measurement. There are nominal variables, ordinal variables, interval variables, and ratio variables. And so we can think of frequency distributions as counting nominal categories because they're things in categories. They're not numbers themselves that we would add together. They're counts of things. So again, if we're comparing males to females in this particular group, we see that there's a total of 40 people in this group. 15 of them are male and 25 of them are female. And, we're familiar with doing those little tallies where we put those little slashes down to tally up the number of people in a group, and then we count those up to get our frequency. And then we convert our frequency to a percentage. First, we can convert it to a relative frequency. So 15 divided by 40 would be 0.375, and 25 divided by 40 would be 0.625. And then if we multiply those by 100, we get the numbers in the last column, the percentages, which are 37.5 and 62.5. We can also tally up categories in ordinal variables. And remember, ordinal variables are like nominal variables, except the categories have an order to them. It has some kind of order from low to high or less to great or something like that. So in this category, for example, individuals might have been asked, how happy are you right now? And their choice of responses would be very happy, pretty happy, or not too happy. And so we tally up the number of responses. We count how many people in each category responded to each category, and we can see that the frequency, the number of people who were very happy, there were 9 people out of 40, pretty happy 25, and not too happy there were 6. And again, if we convert those to relative frequencies, which is the decimal, so 9 divided by 40 is 0.225, and then if we multiply that by 100, we get 22.5%. We can see how the frequencies are converted to percentages for each of the groups in an ordinal variable. And in frequency tables, we can also look at the cumulative distributions or the cumulative frequency distribution. And a cumulative frequency distribution is just a distribution that shows the frequency at or below each category of the variable. And the same with the cumulative percentage. The cumulative percentage distribution is the distribution that shows the percentage at or below the category of each variable. So it's just adding the next variable amount to the previous one. So let's take a look at that on the next slide. Let's look at the cumulative frequency distribution. And on this table, we see the minimum age for each person in the group listed, along with the frequency counts, which are in the second column, the percentages we calculated in each column, and the cumulative frequency, which is just simply adding the second number to the first number. So we're keeping a running total. So the frequency for kids who are 14 was 1, and then the kids who are 15, there was 1. And so if we add 1 and 1 together, we get 2. So that's the running total in that last column called the cumulative frequency column. It's just a running total. And then we have 9 kids in the 16-year-old category. So if we add 9 to 2, we get 11. In the 17-year-old category, there are 4, so if we add 11 and 4, we get 15. And then in the final category, 18, there are 12, and if we add 15 to 12, we get 27. So we get the total number of people in the frequency distribution. So it's really just a running total or a running count of individuals or objects in a particular data set. And on the next slide, in addition to keeping a running total or a running count or a cumulative frequency, we can also calculate a cumulative percentage. Okay, so on this slide then we can look at the cumulative percentage distribution. On the previous slide, we looked at the cumulative frequency distribution, so the cumulative count, or the running count of people in a particular data set. And on this slide, we see the cumulative percentage, which is really just a running total of the percentages. So for individuals in the 14-year-old category, there was one person, and that was 3.7% of the total. And so the cumulative percentage is 3.7 because it's the first one in the list. In the second row, we have the 15-year-olds. There was another 3.7%. So we add 3.7% in that second group to the first group, and we get 7.4%. That's our running total. In the next group of 16-year-olds, there were 33.3% of 16-year-olds. So we just simply add 33.3 to 7.4, and that gives us 40.7%. The 17-year-olds, there were 14.8% of the population. We add 14.8 to 40.7, and we get 55.5%. And then in the final group, the 18-year-olds, there were 44.4%. 18-year-olds, so we add that to 55.5 and we get 99.9%. And as I stated on the previous slide, we do make a note when totals don't add to 100%, or there is always a chance of rounding error. When we're counting frequencies, we can also use frequencies to establish rates. So sometimes we hear about the death rate or the birth rate or the rate of a particular disease. And a rate is just the number that we get by dividing the number of actual occurrences in a given time period by the number of possible occurrences. And so, for example, we all know about the poverty rate, right? So if we determine the 2014 poverty rate, for example, we can get that type of data from the U.S. Census Bureau. And so if we look on the census counts, we can see that the number of men and women in poverty in 2014, the actual occurrence or count of people who were identified as being in poverty, divided by the total population in that year, which is the total number of people who could have possibly been in poverty, we can establish the rate or the percent. And so a rate really is just a type of percent that tells us the number of incidences or the number of cases that can occur out of all possible cases. So in this case, we see that 46,247,000 individuals were in poverty in 2014, and the total population at that time was 308,456,000. And so if we divide 46,247,000 divided by 308,456,000, we get 0.15, which is the proportion. And if we multiply that by 100, we get 15%. So 15% of the population in 2014 were in poverty. So we can say that the poverty rate in 2014 was 15%. One of the skills that you will be learning in this course is how to read statistical tables and how to look at all of the data and put it into context and interpret it. So a couple of the questions that you can ask yourself when you're looking at a table with statistics is, what's the source of the table? In other words, where did the data come from? How many variables are presented? What are the variable names? And what is represented by the numbers presented in each column? And so let's take a look at this table and read through this one. It's the table's title is Selected Economic and Social Indicators for Whites, 2009. And any decent table or acceptable table will have a title. So the title should be informative and it should tell you what is in the table. But you still need to look at the table to make sure that the title is representing what you think it represents. So in this case, we see that the indicators or the variables, we can also call them variables, are things like family income of $200,000 or higher in the last 12 months, people who have a bachelor's degree or higher, people who are below the poverty level, individuals, and people who own a home. So these are selected economic and social indicators for white individuals in the year 2009. And the percentage or the rate in each of these categories for the population, there were families who had $200,000 or more higher. There were 5.7%, or the rate was 5.7%. Individuals with a bachelor's degree, 29.3%, below the poverty level, 11.7%, and people who owned a home, 71%. So that's just really a brief overview of this chapter. On this slide are listed the key terms. You please review these, go through them, take a look at the definitions. And if there's anything that you don't understand, please let me know, and we will review in our next class session. Now on to Chapter 3. Chapter 3 covers graphic presentation of data. So in Chapter 2, we looked at frequencies and how we express those frequencies and proportions and percentages in tables. But we can also represent data graphically. One type of graphical representation that we're all familiar with is the pie chart. And it's simply a graph that shows the differences in frequencies or percentages among categories of a nominal or an ordinal variable. And so the categories are displayed as segments of a circle whose pieces add up to 100% of the total frequency. So it looks like a pie with slices in the pie. And each slice of the pie represents a different percentage or proportion of the frequency of that particular thing that we're looking at. We can create a pie chart from a frequency table. So in Chapter 2, we looked at the frequency table for people who had iMacs and what type of computer or operating system they had before that. And so if you recall, none, there were 0.17 or 17%. Windows were 0.12 or 12%. Macintosh were 0.71 or 71%. And the total was 100%, of course, if you add all of those percentages together. And again, if we look at the relative frequency, 0.17, I say that's 17% because I just multiply 0.17 by 100 to get the percentage. And it's the same for each category. 17%, 12%, 71%, totally 100%. And we can create a pie chart from those frequencies. So in the previous slide, we saw the percentages, and now they're displayed in a pie chart. So people who have an iMac previously had a computer with a Macintosh operating system, and that was 71%. So we see that's the largest piece of the pie. None, 17%, and 12% Windows. And just so you know and remember that a pie chart must always add up to 100%. So, or the total number of count in the population. So you can't have a pie with a missing piece. This is another pie chart based on census data. It's a 3-year estimate of people in the population who are 65 years and over by their race from the years 2009 to 2011. And so we can see the different race categories: Asian alone, American Indian alone, Black alone, white alone, Native, Hawaiian, or Pacific Islander, some other race alone, 2 or more races combined. And next to those, we can see each of the percentages. And they correspond to the size of the slice on the pie chart. And note that, sometimes when the slices are really skinny, there's very few American Indian alone, 0.5%, that we don't always put the numbers in the pie chart because there's not room. So we have to put the categories and percentages outside of the chart and then just draw a little, we call it a leader line, or a little line that points to that part or slice of the pie. And sometimes when we have very small slices of the pie, so let me just go back to the previous slide, we can see that this slice is very small, which is American Indian alone. We see that some other race alone is relatively small slice, and we see that 2 or more races combined. These are all very small slices. And Asian alone is a little bit of a bigger slice, but it's not super big. It's not a real big slice. So sometimes what we can do is we can combine categories if we want to show a larger chunk of a pie. So in this case, 2 or more races combined was kept separate, 0.9%, but all of those other categories that had small slices totaled to 5.6%. So we just made them one bigger slice in a pie chart. And so it's just important to know that when you're creating a pie chart, you just want to decide how you want to present your data and what information is important for your viewers to know. So in this case, in the previous slide, it might be very important for the people you're presenting this chart to know all of the distinct categories, all the different little categories. But for other presentations, it's not so important. You just want to know kind of the major or larger categories or groupings. And so in those cases, it's okay to group these smaller areas together to get, show a larger piece of the pie. We also can use bar charts, and a bar chart is a graph that shows differences in frequencies or percentages among categories, again, of a nominal or ordinal variable, but they're displayed as rectangles or bars of equal width with their height proportional to the frequency or percentage of the category. So the height of each bar relates to how many people are in that category, how many things are in that category, or the percentage of things in that category. And so here's an example of a bar chart. And this is a bar chart, again, of that same chart, or that same frequency table. iMac purchases as a function of previous computer ownership. So in other words, what type of computer did people own before they had iMacs? And none, we can see that this is the number of buyers. So this isn't percentage, this is number. So we can see that it's a count. But a nicer way really of doing a bar chart is to label the bars to show either counts or percentages. And this one shows the percentages of the marital status of U.S. elderly who are 65 or older in 2010. And so we can see that 4.3% were never married. The largest proportion or percentage were married, 57.6%, and then widowed and divorced. And we can also show, bar charts can also show groups together or subgroups. And so in this case, we still have the marital status by major groups. So whether they're never married, married, widowed, or divorced, those are the main categories along the bottom. But then they're subdivided into men and women. And so there's 2 bars in the never married category. There's 2 bars in the married category. There are 2 bars in the widowed category and 2 bars in the divorced category, and each of those bars represents either a male or a female, men or women. And the lighter green are the males, and the darker green are women. And we can see there's a legend at the bottom of the chart, which shows us which color corresponds to men and which color corresponds to women. Another way to look at a bar chart is to look at it horizontally. So the previous chart was vertical, but sometimes when we're presenting data, it's easier to look at it in this way. And the reason is because there are a lot of categories here. So if we presented all of these categories, poker, blackjack, bridge, gin, cribbage, hearts, etc., on a chart that looks like this, we'd have all of these charts along all these categories along the bottom. It would just be too clunky to look at the categories that way. The names would run into each other. So if we flip the chart and we present the bars horizontally, then we can have more categories that we can look at. And it also gives your viewer, a good idea of what the proportions are. And remember, when you're creating a bar chart or a pie chart or any type of graphical representation, you're doing it for your viewer. You want to be able to convey the data in a way that the viewer understands. And so this just simply shows 2 days of the week that people play cards, each type of card game on Wednesdays and Sundays. Wednesdays are blue, Sundays are yellow, and the proportion or the percentage of people who play in each category. Or in this case, it's the count. We can see it's the count because at the bottom we see 2,000, 4,000, 6,000 wouldn't be percentages; they would be counts. And so we can see the most would be played spades. On a Wednesday. That's really the highest percentage compared to people who play spades on a Sunday. You can also develop 3D charts. Again, these are just different ways that you can display your data for your viewer. I'm not a big fan of 3D charts personally. I just like the flat 2-dimensional charts, but there are just different ways that you can present the data that could be more appealing to particular viewers. It's important not to get too fancy, and so, sometimes we see charts in magazines or news articles where they show percentages or proportions by using some type of picture of something. And in this case, the chart shows the number of people who own iMacs, the type of computer they previously owned, by the size of an iMac computer or size of a computer. And so this is nice and it looks interesting. And you also have to be careful too, because in this case, we can see how big this Macintosh is. And so people will think, there were just so many more, like many, many more. And this little Windows is teeny tiny down here. And that's like only an itsy bit of people own Windows. But these sizes aren't necessarily proportionate, because we can see like how wide this is versus how tall this is in the Macintosh and versus this. If we went back and looked at the actual numbers, really Macintosh isn't that much larger than none in Windows. And so that's why when we have bar charts, we say that the bars should be the same width, because we want things to be proportional so that when people are looking at them, they're doing a fair comparison. And in this case, the widths are different. So it's really not a good way to represent things. It's also important not to mislead people by using charts. And we see this all the time in the news and different things. So, for example, in the first chart on the left, the bar chart, we just see our regular bar chart where we show none, Windows, and Macintosh as previous computer owners. And we can see that, there were a lot more Macintosh. But sometimes people will fiddle with the charts and they want to make it look like there were just really, so much more in a particular category and virtually none in another category. And so in this case, what the person who created the graph did was they started the base at 50. So in here we can see 0. It starts at 0 and goes up to 400. On the second chart, it starts at 50 and goes up to 400. So we cut out all of this extra space down here, which just really gives us a little bit more sense of proportion or the percentage. And so we can see that, Windows looks just like a little bit of a sliver, but that's because we're starting it at 50. If we started it at 0, it's a little bit more proportionate. So graphs, charts and graphs can be used to mislead people. So we just have to be very careful about that. And you have to be careful when you're looking at a chart to look at things like, well, what's the base number? And, are these proportions representative? And it's also, telling if there aren't numbers, at the top, like if this doesn't say 561 or whatever, 361 or whatever the count is. If the count or percentage isn't labeled on the bar chart, then we have to really make sure we take a closer look at it, because there might be something that we're misinterpreting. A couple of other things that we won't go into in this course necessarily, but that you may cover in your policy course, would be uses of statistical maps or geomapping. I know one of the software subscriptions that Widener has for the social work department is for Policy Map, and so we can look at different geographical areas, and we can look at different statistics in those geographical areas. So, for example, this lists population distribution, voting patterns, crime rates. I've looked at Policy Map at the geomaps to look at homelessness, different rates of homelessness in different parts of this county and across the state and things like that. So a statistical map really just is a geomap, or a way of showing data on a map. Another type of graph that can show differences in the frequencies or percentages between categories in interval ratio variables is a line graph. We're all familiar with line graphs, of course. And so the points that represent the frequencies of each category are placed above the midpoint of the category, and then they're joined together by a straight line, and then we can look at it. It gives us an idea of what a trend might be. And so in this next slide, we see a line graph that shows the population of Japan, who are age 55 and above in 2009. And so the different age categories are broken down into groups: 55 to 59, 60 to 64, 65 to 69, 70 to 74, 75 to 79, and 80 plus. And so we add up all of the people who are in the 55 to 59 age group, the 60 to 64 age group, etc. And then we plot those on the chart, and then we draw a line to connect them. This is from an annual report that I created for a county who keeps track of the people in their Medicaid program. And so you can see along the bottom, back in 2007, 2008, we had a total of 21,243 people. And by FY stands for fiscal year. Between fiscal year 2011 and 2012, it went up to 22,578 people. So we're counting frequencies, and we're putting them on, we're plotting them on a chart and connecting them by a line. We can use bar charts to show trend too. So this is another type of eligibility chart, similar data to before, but in this case we're showing bars, and so we can see that there's a trend, but it's like a very busy graph. There's a lot going on here, and so it's not as neat and clean, say, for example, as a line chart. A line chart's nice and neat, and you can see the trend easily. This is a little bit more difficult. And then the other problem, there's so many categories here below that they run into each other. And if you recall earlier, I said another way to represent this would be to do it to present the bars horizontally. So we could flip this on its side, and that would make these categories a little bit better. So there's different ways that we can play around with charts to see how they best represent the data in a way that the reader is going to understand them, and that the charts accurately represent the data. There are also time series charts. So sometimes we like to look at variables or things we measure at different points in time, and so it can show things, how things change over time. So it gives us an idea of what trends look like. So, for example, this is a time series chart by, looks like by 20 years, 1900, 1920, 1940, 1960. So by 10-year intervals, the percentage of the total U.S. population who are 65 years and older in each of those 10-year periods. And we can see that this, goes out to 2060, which of course we're not there yet. So there are projections. So this was done, 2004 down here. Key indicators of well-being. That's the data source. So it looks like it probably ended right about here, and they're just projected increase between really 2004 and 2060. We can also use time series charts to compare different categories. And so in this case, we're looking at trend, but we're breaking it down into males and females. So this is the percentage of currently divorced people in the U.S. who are 65 years and older by gender. So we've got two lines. We've got the male line, and we can see that that's represented by data points that are little triangles, and the females are represented by data points that are squared. So the lower line is our males, represents males, and the upper line, or the line that's above that with the squares, represents females. And so that's a nice way that you can use a time series chart to look at change over time, and you can split it out by subgroups. So it could be by gender, it could be by age group, it could be by racial category. And again, just to reinforce that distorted graphs can be deceiving. And so, sometimes I prepare data for individuals, and I give them the numbers, and they look at the numbers and they say, we don't look at the numbers, we want to look at pictures. We want our report to have all pictures. And so that's wonderful and great, because people like to be able to look at something at a glance and be able to interpret it. So we have to be very careful that the graphs aren't distorted, because people oftentimes don't take the time to really look at a graph in depth. And so a distorted graph can be misleading. How we can recognize graphical distortions. So for example, on this next slide, we can see that axes can be stretched or shrunk to create any desired result. And I actually reviewed that with you earlier. So in the chart on the left, we can see that the bottom axis, the horizontal axis on the bottom, where they're listing countries, Rwanda, Sweden, South Africa, that starts at 0. But if we started at 30, then it changes the presentation of the chart. It's the exact same data. We're just changing the way the chart is structured. So it looks like there's more of a dramatic difference between Rwanda and the other countries compared to the first chart. So in reality, the female representation in national parliaments isn't that much different between Rwanda. It's greater in Rwanda than other countries. But the second chart, the chart on the right, really looks like there's a big difference. So it distorts the information. This is another example. Fox News aired a line graph showing the number of unemployed people during 4 quarters between 2007 and 2010. And so it looks like this is just a straight shot up. Boom. 7 to 9 to 13 to 15, like the number of people unemployed is just shooting up. But if we actually look, it's not graphed proportionally. So December 07 to September 08 is less than a year, and March 09 to June 10 is more than a year. So the differences between those time groupings isn't even. There actually were manipulated to make it look like there's this steady increase. And so if we actually plot this out on a chart that is that's proportional, we'll see it look like this. So this is the corrected version. So we can see it's not a straight shot upward. We can see that there's an upward trend. It's not really as much of a consistent increase that was represented on the original chart. And if you want to go use this link, you can copy it down and you can watch it on YouTube. Okay, so when we use statistics in social work practice, the ones that we use probably most commonly to make comparisons among groups or prepare reports for our employers would be bar charts, line charts, and time series charts. So those are good for making comparisons. So why use charts and graphs? Sometimes we lose the ability to examine numeric detail that we can see in a table, and the ability to see additional relationships within the data. And so generally charts and graphs don't show as much nuance as the raw numbers in a table would show. What we can gain is that graphs and charts get readers' attention. And so we can draw our readers' attention to one aspect or more of the information. Some people are really intimidated by numbers. They look at a table and they just see a jumble of numbers. And so sometimes people are just better at focusing on data that are represented in charts or graphs. And also charts and graphs can help you focus on bigger picture types of things rather than minor details. So sometimes if we look at a chart, there's just so much detail there, we lose sight of the bigger picture. So what's really nice to do actually is to provide a table of information and then a corresponding chart or graph. And again, here are some key terms from this chapter. If you have any questions about it, please let me know. We will do a brief review again.